Hi, my name is Zhizhen Zhong. I'm a postdoc researcher here at MIT CSAIL, and I primarily work in computer networks and systems. So most recently, I'm working on a project called Lightning. The project is about using light to accelerate data-intensive applications like machine learning computation. So this project is about how do we actually integrate electronics and photonics and making them work together. The big problem is that people have been using photonics to run large linear computation like matrix multiplication. And in applications like machine learning, where we have a lot of computation that need to be done in matrix multiplication, this is a perfect fit. But for a very long time, controlling the data movement between the electronics and photonics has been the bottleneck of today's photonic computing systems. And our work, Lightning, provides the first solution to this problem. Because electronics and photonics, they speak different languages. Due to the nature of computing with light, photonic computing is passive and it doesn't have computing infrastructures like instructions or memories. So it's really hard to bring photonics and electronics to work together. And to solve this problem, we propose a reconfigurable count-action abstraction. And using this abstraction, we can keep track of the computational dependency graph and know at which stage we should go into the photonics to run a large matrix multiplication. And we will also know at which point we should go back to the electronics to handle the conditional logic. The magic is really our count-action abstraction. And using this count-action abstraction, we build a heterogeneous pipeline across electronic components and photonic components to cooperatively finish the entire machine learning task. So to verify our idea, we also spent about 2 years building the first experimental prototype here at MIT. Our experimental prototype includes photonic computing units and also electronic units like an FPGA. And so by implementing our count-action abstraction into the entire data flow, our prototype is the first one that can serve real-time machine learning inference requests from the internet and running end-to-end at 4.055 gigahertz. And so we are really proud of being able to verify our idea in an experimental system. So as you can see in our testbed, on the right-hand side is our photonic part, where we have this device called optical modulator. It is essentially modulating electrical voltage onto the intensity of light. And if we cascade two of these devices together, we can create a photonic multiplier. And the other side, we have another optical device called photodetector, and its job is to detect the intensity of light and convert it proportionally to the intensity of the voltages. We can use photodetectors to do accumulation that's essentially addition. By combining modulators and photodetectors together, we essentially create a photonic multiply and accumulate unit. And so we can use this part to accelerate large linear computations like matrix multiplication. And if you look at the left-hand side of the testbed, you can see a large FPGA where we are implementing our digital conditional logic and the reconfigurable count-action abstraction. And we also have some RF amplifiers to amplify our voltages so that the voltage going out from the FPGA could be amplified and match the input voltage requirement of the modulators. And so looking at the entire testbed, on the left-hand side, we have an Ethernet interface where we can receive packets from the internet. And the user can send inference requests through this interface. And our count-action logic can identify this user request and abstract the essential information and say, this is a machine learning request. So it's going to kick off the machine learning computation by going into the photonics to run a large matrix multiplication and go back to electronics to do the rest of the nonlinear. And if necessary, it will go back again to the photonics to do the second layer and so on and so forth until it finishes the entire computation. And it can encapsulate the result in the internet packet and then send it back to the user. So this is how our testbed works. So moving forward, I'm determined to enter the academia and then take a faculty job to continue working on exciting research of applying optics and photonics into the computer networks and systems. And at the same time, I'm also looking forward to opportunities to continuously cooperate and work together with the industry to actually find some pathways to commercialize some of the technologies that we are working on in the lab. Generally, I'm enthusiastic about innovations and technology and really looking forward to seeing some of our inventions and ideas could really have an impact and land in our real life.